In this mini-series of videos, you've learned a lot about counting complex arrangements. You've learned some techniques and some tricks for counting, as well as some pitfalls to avoid when solving a problem about counting. There's one finding from what we've seen that really stands out. That's the fact that the number of n-bit strings with weight k is the same as the number of k-element subsets of an n-element set. The fact that these two numbers work out to be the same is a little mysterious because when you look at the objects that are being counted, they don't look like each other. But the numbers are the same, not by coincidence, but because on some deep level, they are just two ways of expressing the same thing. We built a bijection between the two sets to express this. What this bijection expresses is that a string of bits with a number of 1 bits in it is a way of voting from what elements from a set to include in a subset. In other words, these processes, finding n-bit strings of a given weight and finding subsets of an n-element set of a given size, are really doing the same thing. They are starting with a collection of distinct objects and then selecting items out of that collection. The number of ways to take a collection of n distinct objects and select k items from that collection is really what we have been computing all this time. The idea of selecting k elements from a collection of n elements is such an important type of counting problem that we're going to give it a special name. The binomial coefficient, notated like this and pronounced n choose k, is the number of ways to select k elements from a collection of n distinct elements. This is, as we've seen, the same thing as the number of k element subsets of an n element set, which is also, as we've seen, the same as the number of n-bit strings with weight k. Please note this notation is not a fraction. It's just notation, and there's no algebra manipulation we can do with it. For example, 5 choose 3 is 10. We know this because we computed it earlier as the number of 5-bit strings with weight 3. We also know from previous work that there are some special cases. 5 choose 0 is 1 because there is only one 5-bit string with weight 0, namely the string that is all zeros. And there's only one way to select a 0-element subset from the 5-element set, and that's to pick the empty set. This is true for any value of n. In fact, n choose 0 will always be 1. Likewise, n choose n will always be 1 because there's only one n-bit string with weight n. That is the bit string that's all ones, and only one way to choose a subset of n elements from an n-element set, which is to choose the entire set itself. We also know that there's a recurrence relation that governs these arrangements. We learned that for any n and k, the number of n-bit strings with weight k is equal to the number of n minus 1 bit strings of weight k plus the number of n minus 1 bit strings with weight k minus 1. If we phrase this using the binomial coefficient, this would say that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. We can use these initial conditions and the recurrence relation to compute n choose k using a visual trick. Look at this triangle of binomial coefficients. We know 0 choose 0 is 1 because any natural number choose 0 is 1. We also know that 1 choose 0 is 1 and 1 choose 1 is 1 because of our special cases we saw. In fact, all of these numbers along the sides of the triangle are equal to 1 because those are all the special cases. Now look at the highest binomial coefficient we haven't done yet, 2 choose 1. We know this is equal to 1 choose 1 plus 1 choose 0, which is going to be 1 plus 1, or 2. Now 3 choose 1 is 2 choose 1 plus 2 choose 0, which is 2 plus 1, or 3. Likewise, 3 choose 2 is the sum of 2 choose 2 and 2 choose 1, which is also 3. So in this triangle, the recurrence relation that governs how the binomial coefficient works will let us find any binomial coefficient in the middle here as the sum of the two just above it. This triangle is called Pascal's triangle, after the great mathematician Blaise Pascal. For example of how to use this, look at 5 choose 3 again. This is equal, because of the recurrence relation, to 4 choose 3 plus 4 choose 2. Now in Pascal's triangle, 4 choose 3 is the sum of the two numbers just above it, which we've already computed to be 4. And 4 choose 2 is the sum of the two numbers just above it, which is going to be 6. So 5 choose 3 is the sum of 6 and 4, which is 10, and that verifies what we already knew. In this video, we introduce the binomial coefficient, which is a number that gives the solution to two different counting problems: the number of n-bit strings with weight k, and the number of k-element subsets of an n-element set. And we stated two initial conditions for the binomial coefficient and the underlying recurrence relation for the binomial coefficient. And we learned about Pascal's triangle, which is a way to get the value of the binomial coefficient using a visual pattern. In the next video, we'll look more closely at a more general problem of how many ways there are to select items out of a collection when the ordering of the selection makes a difference.